Hello, so in this second video dealing with the dot product and work. Alright, so in the first video we defined the physical principle of work and how to define the work done, alright, which is the same formula for the dot product. Alright, so we extended the formula we had for the work done, which was given by the formula that W, the work done, was the length of the force vector F times the length of the displacement vector D times the cosine of the angle between those two vectors. We can extend that formula to arbitrary vectors, so if U and V are some two vectors in 2 space or 3 space, and theta is the angle in between them, the dot product of U and V is defined to be the number given by the length of the vector U times the length of the vector V times the cosine of the angle in between. And that number could be positive or negative or even 0. So just a couple quick examples of how to compute some dot products, and then we'll do some more with them after that. So this first example, again, we're going to compute the dot product. So what is U dot V? It's going to be the length of U, which is 3, times the length of V, which is 2, times the cosine of the angle in between, which is 30 degrees. So that's going to give us 6. 3 times 2. Cosine of 30 degrees is the square root of 3 over 2. And we could simplify that a little bit. Dividing 2 into 6, we would get 3 times the square root of 3. Alright, for the next example, U dot V is going to be the length of U, which is 5, times the length of V, which is 3, times cosine of 90 degrees. And cosine 90 degrees is 0, so you're going to get 15 times 0, which is 0. We'll give a more geometric interpretation of that in a couple of moments. And moving on to the next example, let's just knock off the next couple. Again, U dot V, we're going to get 1 times 42, those are the magnitudes, times cosine of pi over 4, which is 45 degrees. So we're going to get 42 times the square root of 2 over 2, which would give us 21 times the square root of 2. So we got a couple positive results, 1, 0. The next one, we've got the angle between being 2 pi over 3, so U dot V is going to be the length of U times the length of V times cosine of, in this case, the angle is 2 pi over 3. Our magnitudes, or our lengths, are both 1. So we end up getting 1 times 1, which is 1, times the cosine of pi over 2. In that case, it's 120 degrees. We have a 60-degree reference angle in the second quadrant. Cosine's negative in the second quadrant, so we end up getting negative 1/2. Alright, so can come out positive, can come out negative, can come out 0, as these examples are showing. Alright, moving on now. We've got this definition has a few consequences that are related to it. These are some geometric consequences. Alright, so this is another reason I like to do the version of the definition of the dot product that I showed first, in that we get these following consequences. The first one's true either way, but the dot product of two vectors is a number, not a vector. The next 5 bullets I have here are dealing more with the geometry between them, and has to deal with two things, one being the formula, the other being the algebraic sign on the right hand side. So it's the length of U times the length of V times the cosine of the angle in between. Now, in terms of the algebraic signs, the length of U times the length of V, both of those are going to be positive. So the algebraic sign of the dot product is going to be completely determined by the cosine of the angle in between. Alright, if you think about your graph of the cosine function, cosine starts at 1, drops down to 0 at pi over 2, so it's positive in the first quadrant, and then drops down to negative 1 when we reach pi. Alright, so it's starting at 1, drops to 0 at pi over 2, and then goes to negative 1 when theta is equal to pi. Alright, so it's positive in the first quadrant, negative in the second quadrant. Alright, now these next 5 bullets are a direct consequence of that, and it's that that if you have U and V are non-zero vectors, that their dot product is going to be positive if and only if the angle in between them is acute. Alright, so if it's going to come out positive, then the angle's got to be acute. If the angle of the dot product is going to be negative. That happens if and only if the angle between them is obtuse. That has to deal with the portions that we're talking about. We're positive in the first quadrant, negative in the second quadrant in terms of their graphs. And that's going to make the dot product negative because the magnitudes, as we said a minute ago, are always going to be positive. And the only way the right-hand side of that expression is equal to 0 is if the cosine of the angle theta is equal to 0, and that's only going to happen when theta is equal to pi over 2, or 90 degrees. The other possibilities are when you're going to get 1 or negative 1, and that will happen if the vectors are parallel and point in the same direction. That means the angle between them is 0, or if they point in opposite directions, which means the angle between them is pi. This is the main one to be concerned about, is that two vectors are orthogonal. Orthogonal means they meet in a 90-degree angle if and only if they have dot product 0. All right. So the other two are fairly important. Also, if the dot product's positive, if and only if the angle is acute, it's negative if and only if it's obtuse. All right. And these pictures kind of help us to illustrate that as well. Again, acute, obtuse, opposite, parallel, pointing the same direction, and the 90-degree angle. All right, but the main one to know from that is the middle one, that two vectors are perpendicular or orthogonal if and only if their dot product is 0. So that's an important result to know. All right, and then the other thing we want to talk about is how to use coordinates with dot products, how to determine the dot product using coordinates. So the previous definition is good. I like to start with that, but it assumes that we know the angle between the two vectors, which we're not always going to know. All right, so this is why most textbooks might take the point of view that they're going to define it in terms of coordinates first, and then derive the previous definition in terms of the magnitudes and the angles as a byproduct. Okay, but I like to do it the other way, just because it gives us the physical interpretation, and it also gives us some geometric interpretation in terms of the angles. But this next result is, I just took it out of the OpenStax textbooks that we're referencing. It says if you have two vectors u and v, and they're given as three space vectors, then the dot product is determined by multiplying the first components together, multiplying the second components together, and if it's a three-space vector, also multiplying the third components, and then adding the results. All right, so that's again going to be a numerical quantity, not a vector quantity. If you're just talking about two-space vectors, then you're only going to multiply the first and the second components, and then add. So that's certainly a simpler formula to work with if we know the components of the vectors. So let's get a little bit of practice with these. So u dot v for the first example I have here. So the vector 3, 4 dotted with the vector negative 2, 5. Again, what we're going to do here is multiply the first components, multiply the second components, and then add the results. So we're going to get 3 times negative 2, which is negative 6, plus 4 times 5, which is 20. So we're coming up with 14. And then the next question, is the angle acute, obtuse, or right? It's an acute angle because the dot product came out positive. Let's do the next couple here. U dot v in this case is going to be 2, 1 dotted with negative 1, 2. So again, multiply the first components, multiply the second components, and then add the results. So we're going to get 2 times negative 1, which is negative 2, plus 1 times 2, which is 2. So in this case, the dot product comes out to be 0. And that tells us what? There's a right angle in between the vectors. They're orthogonal vectors, we say also. All right, moving on to the next example. U dot v, in this case we got 3 space vectors. We got 1, 2, 5, dotted with negative 2, 7, and 3. And again, multiplying the first components, the second components, the third components, and adding the results. What does that give us here? We get negative 2 plus 2 times 7, which is 14, plus 5 times 3, which is 15. So we're getting a total of, if I'm doing my arithmetic, positive 27. So in this case, again, we're coming up with an acute angle. Okay, so we got acute angle there. Now, just to finish this video off, we're just going to quickly discuss some of the properties, and this is the theorem I grabbed from the OpenStax textbook. The dot product behaves in a way that you would algebraically consider natural, that the dot product's commutative. It doesn't matter. Okay, sorry about that. The dot product is commutative, and doesn't matter the order in which you do the dot product. It's distributive over top of vector addition, and you could do scalar multiplication in either order, multiply the first vector or the second vector by the scalar, and you would get the same result there. The fourth property is one to point out here. If we add the same vector dotted with itself, we'll just do this in the two-dimensional case, then what we end up with is, say that our vector components are v1 and v2. We got them dotted with itself. And if we multiply them together, our first components multiplied would be v1 squared. Our second components multiplied would be v2 squared. And that's exactly equal to the magnitude squared, because keep in mind that the magnitude of a vector v is the first component squared plus the second component squared for a 2-space vector. The third component would be in there if we had a 3-space vector. So that result follows from there, that the dot product of a vector with itself is equal to magnitude squared.